Welcome back, everybody. Welcome back to the channel. So, I ended up fixing all of the issues for the garbage collector and my multi-threading platform. That's kind of why my videos, like I said, have been a little bit choppy and just on a weird schedule. So, hopefully, we can get back to something a bit more normal. But today, we're going to be talking about the actual garbage collector, so how to build it. And it's just in time because I ended up fixing everything. So what you want to do is create a memory folder in your virtual machine. Now, I know we still have stuff to talk about regarding the multi-threading system. I know we still have to talk about how to set up a thread and also how to start a thread and stuff. To be honest, it really doesn't, like, this is the actual flow that I went through when I was building the programming language. I didn't just immediately, once I built the entire multi-threading platform, just started writing everything else for like executing statements, because you can't execute or do anything unless you don't have a garbage collector. Specifically speaking, if we go to our setup function, you can see here that I allocate a stack element, and I use the calloc function that is required by the garbage collector. And the garbage collector has to be running in order for me to attempt to try to collect memory in order to do stuff. So it kind of is dependent on that in order for it to work. We also have to, be able to resolve objects and like get data and stuff. So that's what we're going to be focusing on. I don't think the garbage collector is too complicated. So let's just get right into it. So what I have is I have what's called a generational garbage collector. Now, I'm going to be honest, the generations used to mean something up until like yesterday, but they don't really mean anything too much anymore. They still have meaning, but you'll see what I mean. But basically, the way it works is every single object has what's called a generation. The generation represents how long that object has been alive, just like in real life, right? So if you have a young object, most objects die young, and I think we've already gone over most of this stuff, but I've made changes, a ton of changes, so let's just go over it again. So like I said, the young generation is going to be the one that dies the most. Then you have adult and old, and then you have the permanent generation, which never dies. They're God objects. So there's that. We now have what's called a GC state. So garbage collection state is kind of what the garbage collector is doing, obviously. So either it's created, running, sleeping, or shut down. I might get rid of this killed. I probably am, so you don't really have to add that. And yeah, so we have that. And then let's see, is there anything else? We also have what's called a collection policy. Now, I used to do different things depending on the collection policy, but now everything's just the same. So this is kind of not really necessary, but if you want to add it, you always can. A collection policy represents how you want to collect the data. So typically before I had low and explicit, and those two would mainly shut down the entire system or stop the world. And we basically do a collection and that's it. And the GC concurrent would just run concurrently and not really slow anything down. So that's kind of how that worked. And after that, so let's see. So we have a series of fields, and like I said, I think we've gone over all these, but let's just make sure. So I have a low memory that I no longer use, so I'm actually going to get rid of that. That was a new change that I added. So we have what's called the GC state or the state. We have the mutex for the GC, the current thread, which this is honestly completely unnecessary. I think this was predated to when I had the ability to just get the thread self. But I have that. And I also have a message queue. This is how we send messages to the garbage collection. This is kind of the standard practice that I do when it comes to messaging threads in my internal system. I also use the same message queue design pattern or whatever for sending data to the actual JIT. We also have, let's see, so we have a bunch of other fields. So I removed some fields. I removed the Y objects, A objects, all that stuff. So you don't need that anymore. We have manage bytes, and these are all atomic variables now because that is better for synchronization. So we have how many bytes we have managed, what is the total memory limit, what is the memory threshold, and how many young, adult, and old objects we have. Now, to be honest, this is now more or less used for debugging purposes. This has no purposeful true value. This is mainly used for debugging, and we'll actually see some really cool stuff at the end of this video, so stick around. I wrote a pretty nice profiler for both my entire programming language and garbage collector. We've gone over it before, but I've made some changes that I think make it really nice. So if you guys want to see that, definitely stick around to the end. And yeah, so then we also have locks. So we want to create a list of locks. That's for locking objects. We want to have a sharp object. This is going to be the head of the garbage collection list, and this is going to be the tail of the garbage collection list. And the way it works is I use a linked list of data to basically make everything work. And then I have a heap size as well. So this is going to be a count of how many actual objects are inside of this, basically this linked list. And again, this is mostly for debugging, so if you don't want to add it, you don't have to. Also, really quick for objects, for sharp objects, I also added a new field to that. It is called, where is it? It's called a monitor. And I use what's called bit fields. And what a bit field is in C++ is basically you can create a field. So for example, typically an unsigned short would have a size of what, 8 bytes, I think, or 8 bits. But since I have this thing here where I say colon, then 1, I'm saying instead of allocating 8 bits for this specific field, I only want this to allocate 1 bit for that field. So this is a quick way to basically save on memory, and I want to keep the size of my objects as low as possible. But basically this monitor is used for a wait and notify system that I just added like today, basically to allow you to wait and notify just like in Java on specific objects. So if we go back to our garbage collector, we have, I think that's everything. So let's actually get into the initialization of the garbage collector. So if I go back to the main file, we can see if I scroll way up to the top, I have this garbage collector initialized, and I mentioned you wanted to create that previously. So what that does is that basically allocates the first object. Now this object is going to be just a dummy object. It's not really going to have any data inside of it. It's just allowing us to basically start the process for our linked list of objects. And if that object is equal to null, then I basically say out of memory, and this actually will cause a bug. So just call regular C++ malloc and you'll be fine. And then after that, I initialize the object. This initialize, I have this on multiple sharp objects. This basically allows you to initialize a sharp object. So basically you want to just set all the default values. Set the info, which is the garbage collection info, to 0. The head, which is just the data for numbers, to null. Next to null, which is structured data. This is completely unnecessary because they're unions. You don't really need to do that. You can just set one of them. So that works. And then you also want to set the size equal to whatever the size is. And of course, set up your info depending on whatever it is. So since this is a generic object, I'm just going to say the info is, it's not a class, so that's K. The type is whatever the type is, whatever the sharp type is. So when it comes to types in my language, I have two. I have whether it's a var type, which means a numeric, or a structure or data structure type, which is obviously for classes and data structures. And then of course none if we don't know what it is. So that's what that is for sharp types. And then you want to set your collection generation, which basically just represents the starting generation of every object. Now I default that to young, but this can obviously be changed. If you set this to a permanent generation, then it will never be collected by the garbage collector. So, and then of course you want to do your other stuff too. I don't really think we have to go over this. And then for set info for classes, the only difference is that I basically pass in the info, I pass the address of the class, say it's a data structure type, and then I basically set the generation to whatever it is. Now this set info is one of many defined statements that I created, which basically allows you to set up information on the actual object. So my sharp objects have a basic bit layout. So it's like 32 bits. So you can basically see here's the format here, and I have a specific amount of bits for each data set. So, we've already gone over this, so I don't think I have to go over it again. But if you guys want, you can always copy the code down from here, or you can basically tailor it to whatever your bit format is for your specific object. So all that code for manipulating the bits is going to be in the garbage collector, and it's going to be right below the garbage collector class. You can find all of these defined statements there. It's pretty straightforward. I'm pretty sure you guys understand bit shifting, so we don't really have to go over that. So once we have all that, then if we go back to initialize, the last thing you want to do is set the tail equal to this value. So this is going to be the head or the starting point of the actual memory. And you want to set the tail to the starting point because obviously this is the starting point. It's kind of like a snake. As it grows, it just gets longer, and you just update the tail. So that's kind of how it works. And once we do that, then we're pretty much ready to go. So we're going to call startup. So when we want to start our garbage collection, we want to create a thread, and we want to say create a daemon, and we're going to create it as a GC. So that's just going to be the name. And we do our standard stuff. We've already gone over creating daemons, but it basically just initializes the thread with the init method that we went over before. So for daemon, I set this to true, and initialize stack, I just left it blank. I think initialize stack is automatically set to false. Yeah, so all I'm doing is I'm saying this is a daemon thread. I don't want to initialize the stack, and I set up the appropriate data. Now, because this is an internal thread in my system, we don't need a main method, so we just set that to null, and that works just fine. So, and then of course we push our thread, and once we're done with that, we just start the daemon. So we call the start daemon function, which we've already gone over, which basically starts it based on whatever parameter or function that we passed in here. So we pass it the garbage collector thread start function, and then we pass it the GC thread, which is going to represent the actual malloc thread that we created for this specific thing in our system. So we call thread start, and that's going to be this main code. So once you kind of have everything set up for initializing and starting it up, you want to create this thread start function, and this kind of has the exact same format as all of our other functions are going to have for internal threads. We're going to have a return type of based on whatever operating system it is. So you can see here for Windows and POSIX, and then it's going to take a void pointer as the parameter. Once this thread is started, we want to set up the thread self, and we want to set the state to thread running. And each thread in our system, whether it be low level or high level, is going to have to follow this same pattern where we, set the states and modify that and everything, because we want everything to work in harmony. Doing this also allows us to not have to differentiate between internal threads and high level threads, because if we assume everything always works the same, then it just makes it a lot easier, like I said. So you want to set the T self to thread self, which is really stupid. Again, you don't really have to do this anymore because I have thread self here. Then you want to set the GC state to running, and you want to set the priority to priority low. Please do this. This is very important. You do not want your garbage collector to have a high priority because it's a garbage collector. You want it to be utilizing as little CPU time as possible. So just keep that in mind. And then we just call GC run, and that's it. Of course, we catch any exceptions, and we say tsig exception is equal to 1, and then we just call thread exit. And then, of course, we return based on what type of operating system. Now, one thing I do want to mention before we continue on, if you guys want, and if you guys, I know some of you may not be able to get a Linux PC as well, or you may not be able to get like a Raspberry Pi, whatever. If you guys ended up getting Sea Lion, and you have a Windows PC, you actually don't have to pay any extra money to basically utilize a Linux PC. The current computer that I'm actually recording this on is actually a Windows PC, but you can see here it's running it as POSIX. And the way that I do that is I basically run this as a WSL or Windows subsystem of Linux. I would definitely recommend checking that out. I will put some links in the description below if you guys would like to add this to C-Line. So that way you can basically pick MinGW if I want to run in Windows mode, or WSL if I want to run in Linux mode. So this is really nice. I highly recommend it. But in the thread exit function, we're not going to go over this now. This is, I guess, one more function we have to go over, but this is a pretty big one. Basically, all it does is it sets your thread up to be exited. So it checks to see if we have an exception at the time of exit that we haven't handled. And if we do, then we basically handle that exception. And this, we do the same thing Java does, where it says unhandled exception on thread whatever, most recent call last, and then I basically print out the stack, basically. So we'll go over this a little later, but let's kind of stay focused on the actual garbage collector. So assuming that you've created this thread exit function and you've returned the appropriate value, now we want to actually run things. My garbage collector is pretty straightforward. It does kind of operate like the Java virtual machine, but in a simpler way. Basically, the way it works is as we're running our garbage collection, let's ignore this code for now. Basically, as we're running it, we're going to check one simple thing. Is it time to collect based on memory? And what this GC collect memory does is we basically want to make sure that our managed bytes, or the total amount of bytes that we're currently managing in the system. If it's greater than our memory threshold, then we basically say it's time to collect, and I collect a GC concurrent. Now, before we get into that function, let's go back up to the top. So in order to make all of this work, we want to hook this code into our standardized thread system. Basically how threads work in my entire programming language, whether it be the garbage collector thread or the just-in-time compiler thread or the main thread or whatever, we basically do a check every time in the main loop if we need to suspend ourselves, if we need to kill ourselves, and then we also check to see if there are any other things that we want. Now, this is custom specifically for the garbage collector, but the basic flow is the same. And something that's very important that I want you guys to realize, this is done on purpose. You want to make sure that you put the suspend check before the kill check. Because the way it works in my system is that basically when it's time to kill all the threads, we're going to suspend them first and then kill the threads. If you guys remember, in the previous episode, I have a suspend, or no, actually I'll go to kill all, right? So I suspend all threads and then I kill the threads by terminating them. So I set the state to killed and that kills them instantly. The reason why you want to do that is because you want to make sure you're suspending them first. That way you know that they're not doing anything pertinent. So we want to give each thread at least a little time to respond. So once we have these things, then for specifically the garbage collector, we want to check to see if we have a message. The way messages work in my language is we basically put a mutex on this messages queue, and we use this mutex to basically send data to this message queue, and we send what's called a collection policy. And basically this is just a way for us to basically say, garbage collector, I want you to do something. So what I do is I say if the message queue is not empty, I create a collection policy variable, I guard the mutex, I pop the last policy off the list, and then I check to see if the policy is not equal to GC concurrent. If so, then I collect. Now, this used to mean something, but all the policies do exactly the same thing, so it doesn't matter. Basically, all you want to do is if there's a message for the garbage collector, you want to collect. That's all you need to know. And here's where it gets interesting. So obviously, we're running in a loop, right? And we're running in a background thread that's also running in parallel with our main thread. You do not want to just run this indefinitely without doing any type of sleeping. If you don't, then your program will never finish because the garbage collector most likely will take up 90% of the CPU time and execution. And believe me when I say that 9 times out of 10, if you're having performance issues, it will almost always be the garbage collector. So this should be your very first thing to look at whenever you're debugging code or issues with your programming language. This is one of the main mistakes that I actually made this week. This is why it's taken me 2.5 weeks just to fix this bug that I've been trying to work on, because I didn't start by just simply looking in the garbage collector and realizing that that was actually the cause of the problem. Keep that in mind. And when you sleep, now you want to sleep a decent amount, but you don't want to overdo it, because if you sleep too long, then you're going to get an out of memory exception. So you want to have a nice balance. I do not recommend you sleeping for 1 millisecond. That is way too short. And I don't recommend you sleep for 100 milliseconds because that's way too long. So I kind of put something in the middle of that. So I put 25. For me, for Windows, the sleep, this basically sleeps for 25 milliseconds, and I call usleep, and I convert it to milliseconds by, doing 999 times 25. So this works very well for me. You guys can use whatever you want, but that's what I have. I also check to see if the state of the garbage collection is sleeping. This basically is a feature that I added later on, which basically allows us to put the garbage collector to sleep if it's just being too much of a pain in the ass. So this is a really nice feature for the high level if you just don't want the garbage collector to run for a specific amount of time. However, sleeping the garbage collector does put you at a greater risk of getting an out of memory exception, so just keep that in mind. And then, of course, this is how we check for the message queue. So if the message queue is not empty, we just go to message. And we don't have to worry about mutexes for reading data. It's only for writing data. That's why I only guard the mutex when I pop it off the list. And then finally, down here, I have my GC collect memory, and also check to see if we have a signal, right? So if we have, whatever type of signal, whether it be a suspend signal or whatever, then I go to signal, and it's either going to be one of the two. It's either going to be suspension or killing it. So that's why I do that, and that's it. So that is the entire main loop of my garbage collector. Now let's actually get into how I do garbage collection in the programming language. Garbage collection, in a nutshell, the way it works is basically every object is, I use what's called a mark and sweep system. The mark and sweep system basically signifies that as we're allocating various different objects in the programming language, let's say we have object 1, object 2, let's say object 2 is referencing data to object 1. And let's say we're in some function called foo. Well, let's say at a certain point, object 2 is no longer referencing object 1, but object 2 is now referenced by some other piece of data. So let's say we have another object 3 is now referencing object 2. This object 1 is now called abandoned memory, or that's just a name I made up. Basically, it means any object that has 0 references to anything. Now, if you guys remember, each object has a reference count field that basically keeps track of that, and it's an atomic integer, so we don't have to worry about, it being 0 and it's really not 0 because threads were stepping on each other's toes. We don't have to worry about that. So what we do is we first come around and we mark it. So we say, we're going to mark 1. And let's say at a certain point, and guys, this is entirely possible, and I will explain this in a second. Let's say at a certain point, 2 now also references 1 again. When I come back around to processing this memory, if it's marked and it now has a reference, I then remove that mark and I continue on looking for other abandoned objects. Now, how in the hell would 2 reference 1 when it has 0 references and it's basically thrown into the ether and 2 has no references to it? Well, that could potentially happen by basically just timing, right? So as we're assigning data, I have these functions here, these inline functions that represent assigning data to another object. And the way it works is I basically, as I assign data from one object to another, I decrement the reference of the current object I'm holding, and then I assign a new object. So theoretically, you could decrement the reference of this object here and then take that object and also assign it to something else in the process, and it just happens very quickly. So that's why we mark it, because we want to be absolutely sure that the object that has 0 references is not simply just being intermittently assigned to another object in some other thread, and we just don't know. So by doing this, it guarantees that if we traverse the entire memory system and then come back around once again, there's a high chance that that object is not going to be referenced again. So that's kind of how it works. And so if I go back to the garbage collector, so now the recent changes that I've made to the garbage collector is I have what's called a DTAS system, a dynamic threshold adjustment system. And that's just a fancy word for updating the threshold when shit gets a little too high. Basically, whenever we're allocating memory, right? And I've done several tests, my garbage collector does not collect that many times. So I have what's called a memory pool sample, and I created a memory pool sample size of 1,000 allocations, or 1,000 collections, basically. So what we do is you want to do this every 1,000 collections. Now, guys, you do not want this number to be low. At one point, I had this as low as 10 collections, and I would update the memory. You do not want to do that. That is updating it way too often, and that's going to bring about serious instability with your programming language. You want things to be consistent, so you want to make sure that 1,000 is kind of a good place to kind of put it. Now, it's going to depend on your garbage collector, but again, just keep that in mind when you're building it. So I have a uint of a memory pool results, and basically what I do is I set the value of the total amount of managed bytes at the time of collection. So every time we're about to collect data, I basically use this sample received field. So if we go back, so every time there's a collection, I say if samples received is equal to the memory pool sample size, I set up or I update the average. But if it's not, which is most of the time, I'm going to set or I'm going to add an entry to the memory pool results based on however many managed bytes we currently have in the system. And what that's going to do is over 1,000 collections, we're going to get a very clean and clear picture of what is to be expected for the average amount of memory that the person is using. Now, what I end up doing is I calculate the average by just for looping through the entire list and adding up the total. And then I just get the average by taking the total and dividing it by the memory pool sample size, which is 1,000. So that's how you calculate the average. And then I do something really cool that I just added like 2 days ago. Basically, what you don't want to do is you don't want to just set the average. I did that for about 2 years, and I don't think that that's a good way of doing it. What I think you should do is set it to the average plus a little bit of what's called a buffer. So I basically add a 15% buffer to whatever the average is. So I basically add the average memory plus the 15% of the total memory limit. So let's say our memory limit is 1 GB. I'll take 15% of that, which is, I'm bad at math. What is that, like 150 megs? I have no idea, but you guys get the point. And I'll basically add that to the average as a buffer, so that way the next time we collect again, we're not going to be always slamming the average because it's an average for a reason. So this is a great way to basically do that. And of course, if the average plus, the 15% buffer is too large, then I just set it to whatever the average is just to be safe. But that's going to be pretty much how I dynamically update the memory threshold. And in doing that, that actually speeds up and slows down the garbage collection because we're only collecting based on whether or not the total amount of managed bytes are greater than or equal to the memory threshold. So this is a very nice way for us to basically control the speed and the frequency of collections in our system. So once you kind of have that set up, then you want to basically do what's called a stop the world collection. Now, this is a very time-consuming way of doing it. Basically, what we do is I suspend all the threads, which basically stops the entire program. So this calls a suspend all threads function. I collect some garbage, and then I resume all threads again. Now, I know you may be thinking that, well, what if you have like a video game or something in the programming language? Isn't that going to take forever? Theoretically, it shouldn't. I've done many tests and I found that it takes on average between 10 microseconds all the way up to 50 milliseconds. Now, I know that's a big range, but typically what I see is the average is usually around 10 microseconds. Now, again, these tests were done on an i7 processor, so it's probably going to be a little bit slower on other processors, but if we're being honest, 10 microseconds is negligible even on an i7. Like if you go to an i3, what is it going to be, like maybe 100 microseconds or maybe 1,000 microseconds or 1 millisecond? That's actually not that bad, and when you pair that with the frequency of collections and my DTAS system, it's really not that big of a deal. So you shouldn't have to worry about that. But yeah, you basically want to do this because as we're collecting, I've been doing tons of tests and I'm going to continue to try to push against this. But if we basically try to, what I used to do was I had an else here. I had else if, what is it, policy is equal to gc underscore concurrent. So if I had gc underscore concurrent, I would basically just call collect garbage without even suspending the entire system. And I would basically be collecting and freeing up objects in parallel with the entire system. Now, this, in my opinion, is the absolute fastest way to do this. But the problem is that you may run into race conditions with fighting against your system, and you're freeing up objects that are still being referenced based on that problem that I mentioned a while ago. So it's a very dangerous thing to do, and I've just found that stopping the entire world is the safer option. So until I can figure out how to properly deallocate objects in parallel, I do this as a safe catch. So now, how do we actually collect garbage? How do we collect objects? So what I do is I lock the mutex. This is very important. You want to lock the mutex and you want to cache the current value of whatever we're processing. So what I do is I get the first object, which I basically set the first object to the heap or the head, and next I set previous object to null, but here's the kicker. I set the end or the last object equal to the tail. And as we're allocating objects, we're going to be updating this tail variable, so that's why we have to use this mutex here surrounding these fields. But this is very important because as we're allocating objects, we're going to be allocating objects very quickly. My programming language is extremely fast, and it's actually significantly faster than the garbage collector. So as we're allocating objects, let's say we have, object here, and then object 2, then object 3. Let's say we have all these 3 objects, and let's say we have a for loop, right, where we're allocating millions of objects. So if we have a for loop, int of I is equal to 0, I is less than 1 million, or whatever, you guys get the point, I plus plus. And here's a perfect example and reason why we need to do this. And I actually was running this program this morning. If we just say new exception, right, and we just create a bunch of new exception objects, and we do this for maybe not even a million. Let's say we did it for like 100 million times. This is basically going to bog down the entire garbage collection system and consistently create objects every time back to back. So the assumption is that if the user is creating tons of objects, anything that's going to be created after the tail at the time of collection is assumed to be a fresh object, and there's no point in wasting processing power to try to check to see if we need to mark those objects, because 9 times out of 10, any objects created after the tail are still going to have references. So that's the long answer of why I cache the tail at time of collection. So I basically have just an infinite while loop which goes through the entire system, and I basically want to just, like I said, free up the objects. So as we're doing this, you want to check to see if the current thread is killed, or if the current object that we're processing is equal to the tail or the cached tail, or it being the last object in the list. Now here's something you need to know. Please do not kill or free the tail. Guys, I've had tons of problems with this. You do not want to free up the tail or the last object in the list, because obviously that's the tail, that's the last object. You will basically end up corrupting your entire memory system if you free up the last object, because then you don't have another tail to assign the objects to. So it puts you in a weird predicament where I basically stop 2 objects before the tail. So let's say if we go back to our example where we have, 1 and then 2, and then we have 3. Let's represent 3 as the last object in our memory list. Basically, I would stop immediately. So I would potentially deallocate this one, and I would basically stop right here. So I would stop at 2 and leave 3 alone, because I know that I still need a tail so that other objects can be allocated later. And in doing this, you don't really experience any performance issues, so it's fine. I've done several tests with my garbage collection where I was creating tens of millions of objects, and it's fine. So basically, the way that I do it is I go through each generation. So I check to see if the generation is less than GC old, less than or equal to. If it's any of these generations, that means that they're worthy of being destroyed. Otherwise, if they're permanent generation, then that means that they're God objects and you just ignore them. So as we're doing this, I want to check to see if the object is marked. So I get the info and I call the marked define statement, which gets the 30th bit and checks to see if that's enabled. And if that object is in fact marked, then I check to see, I do a double check. So I check to see if the object's reference count is greater than 0. If so, I unmark the object, because obviously this was like a race condition or it was accidentally marked. So we do this as a double check, and then otherwise we just free up the object. So before we get into the sweep, this is the actual sweep function that actually removes that from memory and continues on. So whether or not the object is marked, obviously if we sweep the object, we'll never get down here. But assuming that the object is either not marked or we unmarked it, we're going to check to see if the ref count is less than or equal to 0. We're going to mark it, and then we check the generation. Now, this is where it gets into the debugging phase. Now, again, you don't need to do this if you don't want to. In all honesty, you can just do that and you'll be fine. You don't need to do this. I still keep the concept of generations alive in my programming language so that I can debug and test my garbage collector. So I do a switch statement on the info. I get the generation, which calls this. It does a bit shift of 28 and checks the generation mask. And if it's a young generation, then you want to promote that to an older generation. So I say young objects minus minus, adult objects plus plus, and you want to set the generation to an adult object. If it's an adult object, you want to promote it to the old generation. So you want to say adult minus minus and then old plus plus, and set this as a old generation. And once you get to an old generation, you can't be promoted to a God object because that's not how it works. So you just kind of stay being old forever. And we're going to see this later, but this is an excellent way for us to check the effectiveness of our garbage collector if we have a program where it's allocating millions and millions of objects every second, And if basically at the end of the collection, let's say we have young objects of maybe 100, and then we have adults of maybe 1000, but then we have old and it's like 100 million or something like that. That means that we did a poor job at freeing up any of these objects as they were progressing through the generations. So the smaller that each generation is as we progress through it, the more effective it shows that our garbage collector is at actually collecting memory. If both the young and the adult object generations are both tiny and the old generation is just jam-packed with a crap load of objects, then you're doing a poor job. Finally, we want to do our little closing checks. So as we're kind of going through here, we want to set the previous object to object, and then we want to set the next object to the current object. So the reason why you want to do that is as we're allocating objects, so if we go back to our example of 1, 2, and 3, each object is going to be a linked list where we're going to point to the next object in the list, and that's kind of how we basically create our array of objects in our memory system. So once we free up, let's say 2, we're going to need to know what the previous object is. So let's say 1, so that way we can assign the next object of 1 to 3. So that's kind of in short how it works. That's why we need to do that. And here's the check where I basically check to see if we're basically at the last or second to last object. So I check to see if the object is not equal to null and the object's next value is not equal to null. Then I want to check to see if the object's next value is equal to null or the object's next value is equal to end. And that's it. So we've basically, for the most part, gone over the bulk of the code for the entire garbage collector. Now, obviously, there's more stuff we need to do, and we'll go over that code as we come across it. Like, for instance, sending messages to the garbage collector. This function, you just guard the mutex, and then you add a collection policy as a message to this message list, and the garbage collector inspects this value, and it responds accordingly. So like I said, there's other stuff that we can do in here, but for the most part, we've gotten the bulk of our stuff down. Now let's actually look at the sweep function as the last thing that we need to do before we kind of close out. So the sweep function, the way it works is we basically want to free up the actual object, and it's kind of a smart sweep function. So I pass in the object I want to free, and then I pass in the previous object that we had before this one, so that way we can set that previous object's to the next value of the current object that we're actually trying to free. So the way that my garbage collection works is I can't just free up all of the objects that the object references. So like let's say we have, a string class. So if we have a string class and it has a field of data, and let's say it has another field of size and whatever, right? When it comes time to free up this string object and it has no references, we can't free the string object and the data and the size. Where we're going to have to do it is we're going to have to basically free up the string object and then set the data and the size to being ready to be freed up at a later date. So that way when we come around to it, we can basically free it up appropriately because we need to know what the previous object was connected to data in order to free that, and also the previous object connected to size in order to free that as well. Now, in theory, the way it should work, depending on how the user actually allocated the object, 9 times out of 10, the way it's going to work is in the actual object system, we're going to have our string object that's going to be allocated in our garbage collector. And then let's say we have some other objects. So we're going to have maybe 3 objects in between. And then we're going to have our data object and our size object allocated like this. So theoretically, that's kind of how it works if you allocate in a serial fashion. But of course, nothing's guaranteed, so we don't risk it by just doing whatever. So the way I free it is if it's a var, if the type of object is a var, then I basically say managed bytes. So you want to update the managed bytes that we have to size of times object times the size. So we get the size of the current object and we multiply that times the size of a double, because obviously that's going to be what we're freeing. We're freeing up this object here. And I free that. And then otherwise, if we have a data structure, then we go traverse through that data structure and we get each object, we decrement the reference to that object that it references, and this object is null safe, so we check to see if the object is not equal to null. we decrement the reference. We also do the same thing for incrementing references as well. We just do that. So that's what we do. And then we want to do a double check. So if the object is not equal to null and the reference is less than or equal to 0. So if we go back to our string example that we had up here, I'm not going to write it again, but if we have our string object and then our data field, the data field was being referenced only by the string object. So once we decrement the reference from the data field, it no longer has a reference to anything. So theoretically, the reference count should be 0. Nothing should be less than 0, but I do it as a precaution. And then finally, you want to mark it. So you instantaneously mark that field. So that way, if we have the situation where we have, I'm not going to write it again, but if you guys remember where you have the string object as the beginning, and then your other fields as like at some later point in the garbage collector memory list, then we can basically guarantee that this object will be freed instantaneously as we traverse through the entire memory. So this is kind of a hack that I recently just added to free up all the data all at once. Then, of course, we update the managed bytes, we free the data, and that's it. We also want to update the garbage collector. So again, this is for debugging purposes, but I basically do a switch on the generation, and whatever it is, I just basically minus that generation. And I plus this one. That's weird. Okay, so yeah, you want to just minus those generations, and that's it. Then finally, you want to decrement your heap size, update your managed bytes to the size of the entire sharp object, because now we're getting ready to free the actual object instead of just freeing the contents that are inside of it. So we get the next object before freeing the current object, we get its next value, and then we guard the mutex of the garbage collector. We check the lock to see if the object has any locks, and we do what's called a drop lock. We'll get to that in a few minutes. And then we basically set the previous object's next value to the next value of the current object, and we free that object and return the next object based on this field that we set up here. So that's kind of how it works in a nutshell. Otherwise, if the object that we're trying to sweep is null, then we just basically return null. So finally, we have our drop lock function. This is a very straightforward function. All we do is lock the mutex of the garbage collector, get the index of, and I have this isLocker function, which checks to see if a sharp object is equal to the mutex's object, which is up here. So it has a reference to that sharp object. So if those pointers are the same, then obviously that's the same object. And I find that object, and then I basically unlock the mutex, and then I update the managed bytes of mutex, and I delete those values, I remove it from the list based on the index, and I unlock the GC. And that's it. So that's going to be pretty much everything today regarding the garbage collector. Now, as I talked about it in the beginning of the video, I'm actually going to have some bonus content. So this is the end of the video for you guys if you don't really want to stick around. But now I'm going to show you guys something really cool with my garbage collector that gives you insight into how it actually works. So if I go over to my drone project, this is the project that I've been working on for quite a while. I'm actually going to just paste in some code that I just copied. And basically what this represents a ridiculous amount of code that just does a bunch of allocations. Now, to keep this short as possible, I'm not going to do 150 million allocations. That's just ridiculous. It's going to take too long. But I'm going to do a very simple test, 5 million allocations. And I basically am going to allocate the error function 5 million times. And I'm going to do two types of allocations. So this is called a normal standard allocation. This is called an inline allocation. Inline allocations typically assign the fields and objects in line, and it doesn't call any functions. And this is typically significantly faster than this. Don't pay attention to the times, by the way, those are incorrect. But we're going to see the differences between allocating normally, allocating inline, and then allocating, or not even allocating, but just simply assigning a value of a field that we created up here to another field. So we'll see that as well, and we can see those various different times. So I'm going to go back here, and if I go back down to here, I can reset the compiler. Go here, and I'm going to switch back to Windows because for whatever reason, when I run the compiler, it acts very strange on Linux for this PC. So I'm going to switch that, and then we can actually see how long it's going to take for it to run this program. Now, comment down below how long do you guys think it's actually going to take. So I'm going to go back here, and we're going to try to run this again. I'm going to switch back to Linux. because it will actually work with the runtime system. And by the way, I guess I could do my closing comments as well. I will be updating the Sharp Native Bridge. There's a lot of annoying stuff that I've been having to deal with that, so hopefully I can get those things fixed before we actually start talking about that. But yeah, I definitely will be making some pretty big changes to that, and they're not even, I don't think I've even updated that in the actual roadmap, so we'll see that in a little bit. But if we actually run this code now, we can see how long it's going to take for us to basically allocate, what is this, 10 million objects. So it'll be 10 million objects and then just another for loop with a simple object assignment. Oh God, the entire compiler has to compile again. All right, this is going to take a while, so I will join you guys when it finishes. All right, so we're back, and now we can kind of see that it took roughly around 5 seconds to run this code. So if I add my just-in-time compiler, this code where it's taking 5 seconds could very easily jump down to about 2 seconds in execution. So that means that I'll actually theoretically be faster than Java. So this is actually pretty good metrics, and you can see here the differences between an inline creation of an object and by creating the object by calling the constructor, it's completely different and much slower. But now let's actually get a closer look to see what my garbage collector is actually doing. So if I go up here, I'm going to enable my Sharp profiler, and I'm going to recompile this, and it's going to take a really long time for this to compile. So I'm going to be back, but we'll be able to basically see how many times the garbage collector has collected objects, how long the garbage collector took to collect those objects, and more. So like I said, once it finishes, I'll be back, and yeah. All right, so it's running now, so we should see it in a few seconds, and we should get a pretty large printout of what the results are for the actual garbage collector. So I want you guys to keep in mind that this is going to take a lot longer. So you're going to see that this took 20 seconds. As you saw before, it took like 7 seconds. The Sharp profiler is very trashy. It's not a very good system. But the point of the system is not to be performative. The point of the system is to basically allow us to see what's going on under the hood. So we can see here that majority of the time was spent in exception, which makes sense because obviously, even though this ran, I think this ran at like 5.5 seconds. This ran at about, what was it, 1.2 seconds. My memory is terrible. And then what was this, like 100 milliseconds or 100, something like that. So as you can see, those are the various different times. And if we go back to the code, we can actually see that it checks out, right? Like obviously this is going to be a lot longer, so we were inside of that a lot more. And of course we call the throwable because this is actually the subclass to exception, and we have to call that constructor as well to create that data. And then we call get frame info. This allows us to basically do stuff with exceptions. You don't really need to care about that. But as you can see, everything else didn't really take that much time. I mean, I do have a limit on how many functions I track, but basically you can see here all these other functions are negligible. So the total time it took for the rest of these are basically less than 4 milliseconds. So this proves basically where all of the work was going to. And if I scroll down, we can actually see what the garbage collector experienced. So if we look here, we can see that the size of our objects are 32 bytes. You can see that the highest memory that the garbage collector has ever calculated was 10 megabytes, roughly, like 10.8 megabytes. The total objects that we've collected is roughly around 25 million objects. The total managed bytes that we have left, and now here's where you get into how efficient your garbage collector is. We can see that the total amount of bytes that were managed that were left were only 55 kilobytes. So we've basically had a maximum memory load of 10 megabytes, and by the time the program finished, the final amount of data left over by the garbage collector is only 55 kilobytes. That's really good. And we can also see here that the objects left over in each generation are very small. So out of the 25 million objects we collected, we only have 400 or roughly about 500 objects in young, no objects in adult, and about 300 objects in old. And I leave out permanent generation because it doesn't really matter. I only care about these three generations here. And then after that, we have the largest collection. This basically shows what is the biggest amount of objects that we collected in one collection. So this means that we've collected a total of 21,000 objects in one single collection as the largest amount. We've also had a total of 1,300 collections. This is another number that you guys are going to want to pay attention to as you're basically building your garbage collector. Now, you don't have to build this ghetto janky system that I did, this entire system for like tracking functions and crap. The point I'm trying to make here is that you do need to have some type of metrics to know what's actually going on in your system. At one point, I think my garbage collector for this same exact program several years ago was executing roughly around 2 to 3 million collections. That's with an M, 2 to 3 million collections. So that means that the garbage collector was running 100% of the time, and it was not very efficient with collecting memory. So you can see here that we have just over 1,000 collections, and that's why I have that 1,000 collection number, because if we go over the span of 1,000 total collections, it gives us a very clear idea of what we can expect for the program to do over the course of its lifetime. So basically, once you hit that 1,000th collection, we update the memory threshold, and the memory threshold ends up being a decent amount where we basically don't have to collect much more after that. So that's kind of why I added that system. And then we can also see here the total time spent collecting in microseconds. So if we look here, this spent a total of 2.5 seconds collecting. So you see here that we have a total of 20,000. And by the way that I got that value is basically if we go here, we can see that we have this many microseconds took 2.5 seconds to execute. So we ran this program for 20 seconds, and out of that entire time, we only spent 2.5 seconds collecting. So that means that the entire system was down for roughly 2.5 seconds during the entire time of execution. Now, obviously, this number is not going to be that long when we actually run it without this testing system, because obviously it took 20 seconds here, but when running this without the testing system, it takes about anywhere from 5 to 7 seconds. So keep that in mind when you're actually looking at these numbers. This is inflated because this system is just really crappy and slow. And then finally, we have the total time spent sleeping. This is another thing you want to keep track of. We spent a total of, what is it, 35. That math is off. I'm going to have to check that. I've had some issues with keeping track accurately of the total time sleeping. But basically the point is that it spent more time sleeping than it did collecting, and that's what you want. And we can see that the total amount of objects, or the heap size, the total amount of objects that we've allocated over the life of this program is 25 million whatever objects. So this is a very nice way for me to basically keep track of all of this information and have at the end of the program execution, regardless of how long it took, the metrics are what matters. It's not about the fact that this system slowed down the entire execution. It's about, even though it slowed it down, what percentages was the actual garbage collector running in relation to the actual total execution time. So hope you guys enjoyed the video. I know this is a long one, but I wanted to get this out because I made massive changes to the actual garbage collector, and it is very quick now. So I'm definitely proud about that. As usual, if you guys have any questions, as always, put them in the comment section below. We will continue, and now we're kind of at a point, to be honest, where we're going to be bouncing around all over the place. So it's going to kind of get a little messy where I can't really show you guys in the normal straight line sense of how to do things, because everything's connected in the programming language. So we'll just go over functions on a case by case basis. And yeah, so I hope you guys understand. I hope I don't confuse anybody. But of course, if you guys have any questions, you can always email me and I can get back to you as quickly as possible. And of course, if you guys would love to help support the channel, definitely head over to my GitHub repository at androidevcd/sharp. And when you do, definitely watch, star, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. And guys, I would really appreciate it if you guys did definitely watch, star, and fork this repository. I've put a crap load of work in the past 2 weeks. There were some times where I stayed up till 3 in the morning. There were some times I didn't actually eat because I was working so hard to try to make this system as fast and as quick as I can. So that way you guys have the best of the best code that runs fluidly and without any issues. So if you guys want, like I said, I would definitely appreciate it. And of course, if you're curious about anything that I'm looking to add in the future to the language, you can always head over to the roadmap section. And there I write some pretty decent descriptions on various things that I'm looking to add in the future. And this is a nice view to kind of give you a high level look at what I'm doing in real time. So hope you guys enjoyed the video. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.